Hello everyone, I'm Gerhard Krumpl and today I have the pleasure of sharing our research titled Adaptive Temperature Scaling for Enhancing Out-of-Distribution Detection Methods. This is a joint work between the Technical University of Graz and Kestrel I. I am proud to present alongside my co-authors Henning Avenhaus, Horst Possegger and Horst Bischof. Neural networks are usually developed under closed-world assumptions, where it is presumed that the test data closely resembles the training distribution. This similarity enables these networks to achieve high performance. However, in real-world applications, which more closely align with open-world settings, neural networks often encounter test samples that significantly differ from their training distribution. This discrepancy leads models to confidently but incorrectly classify out-of-distribution inputs from unknown distributions. The objective of out-of-distribution detection is to proactively identify out-of-distribution samples rather than allowing models to fail silently. This enhances models' reliability in diverse and unpredictable conditions of open-world settings. To improve reliability in open-world settings, we propose adaptive temperature scaling. The core idea is leveraging information across all layer depths, addressing the varied nature of out-of-distribution samples. We achieve this by computing a sample-specific temperature parameter derived from activations in intermediate layers. The sample-specific temperature is then used to scale the logits to effectively combine class-agnostic features with the class-dependent outputs, thereby sharpening the distinction between in-distribution and out-of-distribution samples. In advancing our understanding of adaptive temperature scaling's inner working to improve out-of-distribution detection, the first step is calculating the sample-specific temperature parameter. This process begins with extracting feature maps from the neural network's intermediate layers, ranging from shallow to deep ones. After that, we reduce the complexity of these high-dimensional feature maps by computing the mean activation across each layer, which effectively produces a single scalar value per layer for subsequent analysis. In a so-called calibration phase, which occurs offline and only needs to be executed once, we repeat this process gathering mean layer activation from all our training samples. This accumulated and valuable data is then used to approximate the cumulative distribution function for each individual layer. At this time, we follow a detailed process. So we start by extracting the mean layer activations similar to the calibration phase. Then we apply the pre-computed empirical cumulative distribution function to assess the similarity of these activations to those in the calibration phase. This evaluation is essential in determining the test sample's alignment with the known distribution. Following this, we compute the sample-specific temperature using Fisher's method to aggregate the layer-wise p-values. The resulting temperature value serves as an indicator of sample types. Low temperatures suggest in-distribution, while higher temperatures indicate out-of-distribution. To enhance the distinction between in-distribution and out-of-distribution samples, we scale the model output with the computed temperature. This scaling simply merges class-agnostic features with class-dependent logits, thereby significantly improving their separability. For out-of-distribution detection, adaptive temperature scaling is compatible with any baseline method that utilize model output for scoring. Adaptive temperature scaling significantly widens the gap between in-distribution and out-of-distribution samples. So using information from the intermediate layers enhances detection accuracy as demonstrated in the figure on the right side. This improved distinction is essential for robust model performance in diverse real-world settings. Our adaptive temperature scaling approach was extensively tested on various in-distribution and out-of-distribution datasets. Here we show selected results of a ResNet 18 trained on Cypher 100. Using maximum softmax probability alongside adaptive temperature scaling, we observed enhanced out-of-distribution detection in 7 out of 8 out-of-distribution datasets. We significantly lower the average false positive rate by roughly 47%. Adaptive temperature scaling compatibility with all out-of-distribution detection methods that derive scores from model outputs is a substantial advantage. The results demonstrate a consistent enhancement in performance across all evaluated baseline methods. We also analyzed the role of shallow and deep layers in computing the adaptive temperature. The findings indicate that the best layers vary based on the specific in-distribution and out-of-distribution datasets. For instance, shallow layers are more informative for datasets like street view house numbers, while deep layers are beneficial for the cropped version of the large-scale scene understanding dataset. Consequently, we used layers from across the entire depth of the model to ensure robustness against the diverse characteristics of out-of-distribution samples. In conclusion, our research introduces adaptive temperature scaling, a novel post-hoc method designed to significantly improve out-of-distribution detection. Adaptive temperature scaling uniquely employs intermediate layer activations for calculating a sample-specific temperature, a methodology not only simple but also highly effective. Its compatibility with all baseline methods that derive scores from model outputs like logits or probabilities significantly broadens its practical application in the field. Across various models and dataset configuration, adaptive temperature scaling has consistently demonstrated its capability to improve the performance of all tested baseline methods. Thank you for watching. For more details, please refer to our paper. The code is accessible via the link provided below.